This mini lesson is going to be on systems of equations. Now let's do a little reminder work here before we start. How did you learn to solve a system of equations? Well, first of all, why are we doing this? When we solve a system of equations, we want to know where two lines meet or intersect on a graph. We're looking for that intersection point. Do all lines have intersection points? No. What kind of lines are those? So we could have some answers that don't have any intersection points because the lines are parallel. Or we could have some lines that have infinitely many intersection points because they are in fact one and the same line. So we have three choices when we solve a system of equations. We can get one intersection point, we can get no intersection points from parallel lines, or we can get infinitely many intersection points because the lines are on top of each other. Now, how did we learn to solve these? One is substitution, and that's what we're going to do first here. This one lends itself well to substitution, and the other method you may remember is called elimination, or some of your teachers may have called it linear combination. Hopefully that's ringing a bell for you. This one really lends itself well to substitution because one of the equations is easily solved for one of the variables. If you look at this first equation, it's very easy for us to solve for x or y. I'm going to choose y. I'll change this to y equals 6 minus x. Just subtracted the x from each side. Now, why do you think it's called substitution? Because guess what we're going to do now? We're going to substitute. In the second equation, instead of y, we're now going to plug in 6 minus x. So we get 3x minus 4 times, what did we say y was? 6 minus x equals 4. 3x minus 24 plus 4x equals 4. 7x minus 24 equals 4. Add 24 to each side. 7x equals 28. X equals 4. Now let's think about this to see if we're done yet. When I said we're going to solve a system of equations, what are we looking for? An intersection point if there is one. Is x equals 4 a point? No. Every point has an x and a y, so that's half of our answer. We're going to take this point, or this answer, x equals 4, and plug it in back up all the way at the top. Way up here again. So we had y equals 6 minus x, and now we know what x is, don't we? Y equals 6 minus 4, so now we know that y is 2. And every solution must be written as an ordered pair, x comma y. So now we know that the answer is 4 comma 2. That is the point where these two lines would intersect. And we'd really be silly if we didn't plug that into our two equations and make sure that x is 4, y is 2 didn't solve them. So is 4 plus 2 equal to 6? Yes. Is 3 times 4 minus 4 times 2 equal to 4? 12 minus 8 is 4? Yes. So 4, 2 is correct. That was substitution. This one, you could do substitution if you wanted. This first one's easily solved for y. The second one's easily solved for x. But we're going to do the second method, the linear combination or elimination on this one. Both methods will always work on any problem, but one will typically be easier than another. When we do linear combination or elimination is the name that I prefer because it makes sense we're going to use it to eliminate a variable. Which one would be easier to eliminate, x's or y's? I'm going to say the y's because one is already positive and one is negative. If I want to eliminate this negative 2y, I need the top y to be a positive 2y. So when I add positive 2y and negative 2y together, my y's cancel. So I'm going to multiply the top equation by 2. And in elimination, every term of that equation has to be multiplied by 2. 6x plus 2y equals 22. The second equation we don't need to change at all. And we'll add these together. 7x equals 28, so x is 4. Once again, is x equals 4 the solution to a problem? No, because it's only half of a point. So now I'll substitute that in where x belonged in either equation. So now instead of x minus 2y, I'll write 4 minus 2y equals 6. Negative 2y equals 2. And y equals negative 1. Still haven't written an ordered pair. What's the ordered pair where the points meet? 4, negative 1. And I want to check. So is 3 times 4 plus negative 1 equal to 11? Yes. Is 4 minus 2 times negative 1 equal to 6? That'd be 4 plus 2. Is that 6? Yes. Guess which method we're going to use here? Easy, right? It's already set up for substitution. So now we'll say negative 6x plus 3 times, we know what y is, 2x minus 3 equals negative 9. Negative 6x plus 6x minus 9 equals negative 9. What are we left with now? Negative 9 equals negative 9 because negative 6x and 6x canceled each other out. Is that true or false? That's true, right? So this isn't just going to be two lines intersecting at a point. So that leaves us with one of our other solutions. It's either parallel, meaning there's no true solutions or intersections, or the lines are on top of each other, meaning there's how many intersection points? An infinite number of true solutions. So if our answer is just something that's true, what do you think it is? Same line. We call this a dependent set of lines. They're dependent upon each other. They're right on top of one another. Last example, okay? This one looks like a good example for elimination to me. You can also use substitution if you want to solve that first one for x. Okay, I'm going to multiply my first equation by 3. So that'll make the first one 3x plus 6y equals 12. And the second one, negative 3x minus 6y equals 12. Okay, we add those up, and what do we get? 0, 0, 24. So 0 plus 0 equals 24. Does 0 equal 24? No, that's false. What kind of lines would give us false solutions? We don't have anything true for where they intersect. That would be parallel lines. And we call those an inconsistent system. Remember that they have no consistency between them. Keep working on these and they'll get easier all the time.